So welcome back, everybody. And the topic today is a topic which is going to rotate around more than just one theme. So we are going to go back a little bit to the discussions of setting up our own neural network code for project number 2. So we're going to repeat some of the small details which are needed in order to set up the neural network code. Then, when we have this, we are going to apply this to the calculation of differential equations and partial differential equations. And this is a big topic in implementations of machine learning algorithms to solutions of systems like systems of coupled differential equations. And this leads to a field which is often called physics-informed deep learning, because often you would have differential equations of the type Navier-Stokes, which you would have in fluid mechanics. It doesn't need to be physics-informed, but you can actually let the specific scientific case inform the neural network about different boundary conditions, the constraints, symmetries you want to include, and so on and so on. So this is actually a very active research field. And we are going to scratch the surface, but I wanted you to see how you can actually solve differential equations using deep learning methods. And most likely, many of you will dive into this topic when you're dealing with your master thesis. Solving differential equations is pretty common, whether you're doing geology, whether you're doing life science. If you're doing mechanics, for instance, it's pretty common to solve multidimensional differential equations. And in the last decade, solving this type of equations with the non-conventional methods, that means deep learning methods, has actually acquired quite a lot of momentum. So this is a topic which we also leave as a kind of open path in project number 3. And many people have actually been interested in using differential equations and studying them by solving them by numerically by deep learning methods. So that's actually one of the paths in project number 3. Now, the other thing which we need to look at, and that is to implement the setup of a neural network solver using TensorFlow. So TensorFlow is a library, or a package, you might say, in Python, which has been developed by Google, and it was released first in 2015. Now, TensorFlow is not that different from PyTorch, if you're familiar with that. So PyTorch was released by Facebook. And these are very popular libraries which allow you to implement deep learning methods. Now, what TensorFlow provides is an interface to TensorFlow, which is called Keras. And that's an API. And that allows us to actually set up things in a much, much simpler way. And we are going to see how we can do that, because this is something which can be useful when you're testing your own neural network code against some benchmarks like those provided by TensorFlow. It's always useful to benchmark your own code against what other people have developed. Now, one of the reasons why we want you to write your own neural network code is simply because we want to demystify what a neural network is doing. And if you had time to look at the videos from last week, there's one of the sessions deals about the backpropagation algorithm. So the backpropagation algorithm and automatic differentiation is actually the connection between these two is something which is under-communicated in the community. So automatic differentiation has two modes. One, you move forward, or you move backward. The backward moving is called reverse mode, and that is the same as backpropagation. So one of the reasons why we do backpropagation is that sometimes it's easier to calculate the derivatives because you start with the output. And typically the output has a lower dimensionality than the input. So if you look at a classification case like this handwritten numbers, you have 10 types of numbers. So that means that your output layer has only 10 different possible outputs. So that means that when you connect that with the last hidden layer, that means that you will have much less weights to train. So calculating the derivatives then is normally something which entails less operations. Normally less operations can lead to less probability of loss of numerical precision. So propagating backward has some benefits. And the reverse mode is also one of the standard modes for automatic differentiation. And you will find links in the slides here to general articles which connect automatic differentiation with a backpropagation algorithm. So I don't know if you had time to look at the lectures from last Thursday, the video and the handwritten notes. That tries to give a kind of link between backpropagation and automatic differentiation. So this is actually a very interesting topic. You will also find many other videos which you can look at if you want to. And if we get time, tomorrow we will start scratching the surface of convolutional neural networks. But what I wanted to do now is more to bring back some of the basic elements which we need when we are setting up a neural network. And I'm going to do that by looking back at the slides from week 41, where we look at the setup of our own neural network code. And then I'm going to use that one in solving differential equations as well. So let's do a small repetition of some of the basic things. And I'm going to switch to the Jupyter notebook here. So let's just do that immediately. So the slides from last week, if we now scroll back a little bit and start looking at the basic ingredients which we have to think of when we are setting up our own code. So the first thing we have to do is actually to set up and collect the data, pre-processed data. If you look at the cancer data, which is the classification problem in project number 2, this is already done for you when you use scikit-learn. And that follows much the same line as you've seen in the examples here with the MNIST data, the handwritten numbers. So that means that the first step here is something which we, in this course, typically don't spend so much time on. The other set of data is actually this polynomial, which you're going to feed in order to do a regression problem. So if you feel tempted, you can also look at the Franke function, you can look at more complicated functions, and then try to implement those as well. But there is no, I mean, if you want to do that, it's something you can do. And I've seen that many actually have included the Franke function already in the setup of a neural network. But then we have to define the model and the architecture. So model and architecture are in a way synonymous here, in the sense that if you think back to what you did in project 1, your model was a polynomial approximation. The model now becomes the architecture of your neural network. So when you are studying model complexity now, it would be as a function of number of hidden layers and the number of nodes in the hidden layers. And then another piece which enters your model is the activation function. So these are typical quantities which now enter the setup of your model. So when you do regression, and I'm just repeating some of the things because sometimes it can be useful. When you do regression, if you look at your output layer, then you never have, or very seldom, do you have an activation function on the output layer. So that means that what you produce as an output from each node is actually used as the output to compare with the target values. Whereas if you do a classification problem, like this 10 written numbers, what you would do then is to have a typical function like the softmax function, which then modulates your output so that you can say that if my output is less than 0.5, I give it the value 0. If the output is equal to something larger than 0.5, I put it to 1. So that would be the case of a binary calculation. So the architecture is a very important thing. Then we need to choose cost functions and optimizers. And this, again, gives you a lot of flexibility. And actually, you writing your own gradient descent is something which is very useful, because then you can actually see how fast the methods actually converge if you do, for instance, momentum gradient descent. And some of you have already seen that if you do a momentum gradient descent, that can actually speed up the search for a minima with perhaps at least a factor of 2, at least. And I've seen people having factors of 10 as a speed up by using momentum gradient descent. That's just a simple trick. Then we obviously train the model, and then we evaluate the performance on test data, and then we have to adjust the hyperparameters. So what I want to do now is to bring back some of these elements and re-emphasize them, and then look at their weak points, their pros and cons, so that we have a kind of a critical way of assessing what we are going to do in project number 2. There's another thing I wanted to say, is that in project number 2, there is also the task of writing a logistic regression code. Now, this may seem overwhelming, but a little bit of thinking will tell you that you don't need to write a logistic regression code. Why? Any good? Yeah? Could you say again?
We can use the neural network with the segment function.
So, in the last task, we want to use logistic regression, but when you have written a neural network code, if you take away the hidden layers, so a logistic regression for the classification case is like a neural network without hidden layers. So you would just feed in the input, and then you have the output, which is modulated with, let's say, logistic regression, no, the sigmoid function. So that means that if you make the code versatile, so that you can decide how many hidden layers you have, you don't need to write a code for logistic regression. And that's important. So we've gotten questions about that, and I think it's this is something which is going to save you time. You don't need to write a logistic regression code, because a neural network with no hidden layers, and for a classification problem, where you then spit out in the output just a sigmoid modulated output, that gives you logistic regression. So that should save some time. And since we had a small delay with project number 1 when it came to the deadline, we will probably make a small extension to the deadline here as well. So you've probably already seen that my attitude to deadlines, I mean, the deadlines are for your planning, but we always have some flexibility, because we are after your insights. That's the most important thing. Okay, so these were the things which we need to set up. And if I now scroll down here with this MNIST data set, so I'm just going to rerun some of the codes here because I didn't do that. And you see that the data set is not of an impressive quality. These are pretty blurred images. And the reason why I do that is simply of these with the time I would need to run the calculation. So this is something which I can do easily within the lecture here, without you having to wait and listen to me cracking a lot of lame jokes while we are waiting. So this is the test case which we looked at. And then we split everything into test and train as usual. Scikit-learn is then used to do the train test splitting. In this particular case here, we now end up with 1,400 images for training and 360. So the design matrix now has, along the rows, all the images, and then the columns are the features, and they are the pixels. So in this case, it's 8 times 8, which becomes 64 pixels. And with 1400 images, roughly, you have a matrix, a design matrix of 1400 times 64. Now, you quickly see that in imaging, these dimensionalities can become huge. And as you see from the quality here, the quality of these images is definitely not impressive. And if you go to high resolution, you would have an image of 200 times 200. And then if you have 200 times 200 pixels, you have 64,000. No, so 40,000. And then if you then have 1 million images, then you see the dimensionality of your design matrix. And this is actually where convolutional neural networks kicks in. Yeah?
Don't you have tricks like pooling layers and stuff like that where you can keep some
So what we are going to look at next week and also towards the end of this week is convolutional neural networks, where actually these things come in. So when you look at neural networks in general, the way we are looking at them now, they normally deal with the dense matrices. So these are normally called affine transformations because you have your input data multiplied with the weights and you keep the full density. But then you can actually start thinking of how can I reduce the dimensionality. So convolutional neural networks is actually a way to reduce the dimensionality of the problem. Okay, so when you have defined the model and architecture and you've set up your input data, then the first thing, as we discussed, through the lectures last week, is actually to define the feed-forward pass. And one thing which we also need to discuss a little bit, and we are going to come back to that, is the setup of the weights and the biases. So in this specific case, we have one hidden layer, and then we have one output layer. So we have the hidden weights, which are normally set to some random number. And then we would have the same with the biases. And normally people would set them to a random number according to the normal distribution, or just fix it to a given number. So the weights and the biases are the parameters which we need to optimize. And then we do the same thing for the output layer. So if you're adding more layers, you would actually have to simply set up the weights and the biases for the different layers. This is the initialization part. And typically what is done is that you include a normal distribution, and then you try to find small values for the weights, and you put the bias to some given small value in case the weights are 0 or close to 0, because that will stop your training. So one thing you need to keep in mind is that when you set up a neural network, now you are not driving the gradients to 0. So you want to keep a finite value for the gradients, because else your weights and biases will be driven to 0, and the training will then stop. So the term you compare with after every iteration, so one iteration is the same as you doing a feed-forward pass and a back propagation pass. That's one iteration. Then you get new values for the weights and the biases, and then when you make the new feed-forward pass, you compare your cost function and you look at the optimization of the cost function. So that's the quantity you're going to have as a condition for when you want to stop the iterations. So you should not now, as you did with project number 1, drive the gradients to 0, which is the condition for you finding the optimal values for the parameters, but you're actually going to look at the way the cost function changes as a function of iterations. And when the cost function has stabilized, that's when you would typically stop the iterative process. So we would have the feed-forward pass where we perform this mathematically. These are called affine transformations. So in essence, these are matrix vector multiplications, where we keep the full dense matrices. And as you will see for images, for recognition of images, where you have tons of pixels and millions of images, like in ImageNet, there are millions of images, this becomes very inefficient. So in a way, this is going to motivate, the way we're doing now is going to motivate the introduction of convolutional neural networks. So we have a feed-forward pass, and the basic ingredients are matrix and matrix vector multiplications. We feed this into the activation function, which then gives us an output, and this is fed into the next layer. So in this specific example, and you guys should feel free to use these programs, and keep again in mind that the programs which we have, we try to write them in very simple, straightforward way. There is no kind of complications or fancy things. I just try to keep them as simple as possible so that you can read off the algorithm by looking at the programs. So that's just one way of presenting things. And in this case, we have the, as you can see here, this would be the input to the activation function of the hidden layer. So it takes the hidden weights plus the hidden bias, and it produces an output. Now this output, this A of H, is fed into the matrix multiplications or matrix vector multiplications for the output layer, and then you get an output, ZO here, which then is fed into the activation function for the output layer, which in this case is the so-called softmax function, which is actually a modification for those of you who have studied physics and chemistry. Is actually a modification of the Boltzmann distribution. It's nothing but that. And then we can make a prediction. And in this particular case, when we just have one feed-forward pass, we actually miss poorly. The prediction for the number of, our prediction is number 8, whereas the correct labeled image is actually number 6. And then I'm not going to repeat everything here, but we would typically also include the regularization. We would then include a stochastic gradient descent, which is pretty common, and that's where your code for the stochastic gradient descent comes in. And if we then scroll down here, what you would find then is a typical feed forward and back propagation pass, where we now also have the back propagation ingredient, which comes in here, where we calculate the gradients and update the weights and the biases. And then we can compare everything as a function of the learning rate, which now becomes a parameter. So you can see now that the old accuracy in the training data is not, and the new one are not very impressive. So that means that we have to improve performance. And typically what we would do, and we are coming back to how you can do this, is that we need now to run calculations for different hyperparameters and different learning rates. So in the codes here, I haven't included any kind of momentum gradient descent or any kind of adaptive learning rate, because this is where we want you to actually plug in these ingredients when you have your own gradient descent code. So when you improve both performance, it means also to have slightly better ways of optimizing the learning rate. So what I'm doing here is simply to feed in a learning rate, a list of learning rates. So this is not very advanced. So typically, many of these libraries, they will typically include by default some adaptive way of doing that. But when you look at then the improving the performance here, there is a kind of generalization of the code in terms of a class, which includes the feed forward part and the back propagation part. As you can see here, there's a back propagation piece, there's a feed forward piece, and then we are simply setting up the loop over the, this contains a stochastic gradient descent, by the way, but this is now run with simply just one set of lambdas of hyperparameters and learning rates. And typically what you would do then is now to define the accuracy, which is a typical parameter or score, which you use to find out whether your classification problem is running correctly. And in this specific case, what I'm doing now, I'm running with 100 epochs and have a batch size of 100. And then I simply rerun my network. And in this case, the score is getting better. And then I adjust the hyperparameters. And in this specific case, I'm just going to run through it. So just to show you the results here. And the calculations are pretty fast. And after we've run through the calculations, we can visualize it. And if you haven't used Seaborn yet, as a software to visualize heat maps, try to use it. It actually gives a very nice way to display the data which you obtain. So if we then plot it, so this should have gone through everything now, I think. Let me see. No, it's still doing some runs here. This should be the last learning rate. So normally you would never put the learning rate to 1. So this should actually contain, no, it's still running here. Yeah, this should be, I think this is the last one, yeah. Yeah. So the way you can display this with a Seaborn is actually pretty useful. As you can see here, we have the different learning rates on the y-axis and the lambda values on the x-axis. And this case here corresponds to roughly a learning rate of 10 to the minus 2. And in this case, we do pretty well on the training. So it's an accuracy of 100%. And then you can look at the quality of the test accuracy. And in this specific case, we are getting something which is close to 96% for this value of the hyperparameter lambda. So this is not so bad. I mean, the human roughly gets 98% on these images here. Then, as you probably saw from the videos from last week, we can run this with a scikit-learn's multi-layer perceptron model. But let's try to take a look at what you can obtain with TensorFlow and why TensorFlow can be useful for us. Because it allows us to actually add a lot of functionality in it, and we can test our own code with the functionality which you have in TensorFlow, but you could do the same with scikit-learn for this specific case. But TensorFlow is really dedicated to the implementation of deep learning methods. So let's skip this one, but let's look at the TensorFlow here. And there is an example where I actually repeat the same calculation with the MNIST data set. And you can see in this particular case, it's the same data set, and I'm going to do the same setup. Now, if you want to use TensorFlow, there are 2 ways of doing that. One, you can use TensorFlow as almost like a programming language. So it has NumPy, it has all the same kind of optionalities which you would write in a standard Python code, but then you would have dedicated TensorFlow operations in addition. So that becomes like writing programs with TensorFlow. Or if some of you are familiar with PyTorch, so has any one of you used PyTorch? Okay, so you should feel free to use that if you want to. If you're familiar with it and you find that easy to do, please do that. Now, this becomes quickly a little bit more time consuming because it requires some time to get into it. So what we normally recommend, in particular when you want to look at convolutional neural networks or recursive neural network or more advanced methods, is that we use Keras, which is an interface to TensorFlow. And that allows you to set up a neural network calculation in a very easy way. And that's the kind of approach which we normally recommend in this course, unless you want to write it in PyTorch or use TensorFlow itself. So TensorFlow is more or less like PyTorch. Many people tend to prefer PyTorch because it's more Python-like. Whereas Keras just gives us this interface. And in this course, where we put more emphasis on writing your own code, it can just serve as a way to compare your code with what a professionally written code gives. But let me show you some of the functionality which you have. So this is for a neural network. So you have to define some of these quantities, like the number of layers. So you have this is given by the input package, the type of models, and we are dealing with a sequential model. So you go from input layer, next layer, and so on. And then we want to do a deep neural network. we can import types of optimizers. So they have all the optimizers we have been discussing, like Adam, Adagrad, root mean square propagation, and so on. So these are options you can plug in. And then you can also define the type of regularization you want to do. And what you have here is actually the way you want to output the results. So the categorical one means that you're dealing with a different given classification problem with a set of classes. In our case, we have 10 classes, the 10 handwritten numbers. So again, we will do the same stuff as before. We do a train test split. You define the number of epochs and the batch sizes. We define 2 layers with 100 neurons in one and 50 in the other ones. And then we have 10 categories. And again, we specify the hyperparameters. Now, TensorFlow has also the possibility to do a grid search. In this case, we're not doing a grid search. We just start with the parameters, and then we have a standard optimizers which you can specify. And you see now the way you would set up things here. So in this specific case, we are setting up, we create, this is my function here, and we add one dense layer, which has the 100 nodes or neurons. The activation function is a sigmoid function. And then we have an L2 regularization term. So these are all things you can specify as an input to Keras and then TensorFlow. Now, this is useful to look at because when you're writing your own code, you can think a little bit about the way you want to set up your own neural network. So which are the things you need to specify? Yeah?
How do we choose the number of hidden layers and the number of nodes?
So, yeah, this is a very good question. For those of you online, the question is, how do we choose the number of hidden layers and the number of nodes? So this is actually something we would have to play around with. So there is no a priori a magic number of hidden layers and nodes. So what you will see in this case is actually this case with 2 hidden layers is going to give a worse result than the one I had with 1 hidden layer. And that clearly tells you that perhaps this MNIST data is okay with just 1 hidden layer. So you would actually have to play around. So you can think of the architecture, which is equal to the model. That is something which defines the complexity of your calculation, like you did in project 1 with the polynomial degree. So this is one of the, one of the things that we had many people who were so disappointed when they saw the parameters, because you thought that this was really some black magic which did the job for you. But you have actually to look at parameters like the number of epochs, the batch sizes, and you're probably seeing this when you have tried your own gradient descent, that the results may be sensitive to the number of epochs, the number of the batch sizes, and so on. So what you would have then here is a way to test it. So you can rerun it with less hidden layers or more hidden layers. You can increase the width, have more nodes, etc. And then you define also the optimizer. So the optimizer becomes also one of the parameters you will play around with, or one of the functions you will play around with. In this specific case, since we have a 10 categories we want to classify, we typically use the softmax the softmax activation function. The accuracy the metrics we want to use for the score is the accuracy, so that's specified here. So the optimizer here is a stochastic gradient descent, and that receives the learning rate as a parameter. And you can clearly change that with other types of performing the gradient descent method. And all the functionality which we have discussed earlier with different adaptive methods, that is included in TensorFlow, it's included in PyTorch. All these libraries have that. And then you just rerun the calculations. You run over the learning rate values, over the lambda values, and then you would get something which looks like what we had before. And if you look now at actually this took a little bit more time, and you see now that you have a larger span for the training rate than you had with the with the scikit-learn model for the training part. But then you also have a part here for the set of values for lambda, the hyperparameter, and the learning rate, where you get a 98% score. So this is actually not so bad, but you would have gotten the same with just one layer. So this kind of trade-off is something you have to explore. Clearly, if you have more and more hidden layers, the training becomes much more expensive. So there is always you, which has to strike a balance between the number of cycles you want to spend and the accuracy of your calculation. So I put in this the breast cancer data, which is the data set we propose for project number 2. So I invite you to take a look at that one when you're writing your own code. You could just compare that with this Keras implementation. And there are some useful things here, which I did in this code here, which can give you a little bit more insight. Actually, this is a very popular data set because there are actually quite many people who are interested in these type of problems. And here I've done some simple visualizations where I look at some of the parameters like the mean radius and the mean perimeter. And you can actually make nice plots of these before you do the training. And this should have, so this is actually the training here. And you can make plots of, this is before you do the training in terms of number of epochs and et cetera, et cetera. So you see the calculations being gone for some time here. But if we scroll up here and you look at this Jupyter notebook, you will see plots of some of these parameters. And if you look at the mean radius as a function of the mean texture, that's one of the parameters you can look at. Then you have other quantities like the mean radius against the mean perimeter. So what you're plotting here is the mean radius against the perimeter, and they are strongly correlated. And you can see that because they lie on a straight line. And the blue dots are actually indications of a benign tumor. And the red ones means that you have a malignant tumor. So the size of the tumor due to the mean radius is something which is very much used by a pathologist to say something about whether this could be a bad tumor or a benign tumor. So these are things, take a look at when you're analyzing the breast cancer data, if you wish to, you could look at some of these parameters. So the breast cancer data, which you're dealing with in project 2, or the one we suggest, has something like 30 features. So the perimeter, the radius, the surface texture, the thickness of the tumor, and so on, are features which are included in the data set. And the output in that case is a binary output, and it's only 1 or 0, that means benign or malignant. So, and when you're writing your own code, you can easily compare that one to the calculations which you see here. So I hope that can serve as a kind of inspiration for what we are going to do in project number 1. Now, the thing which I wanted to bring up here now is a little bit about additional things. Because at a certain point, when you've written your code, you ask yourself, I mean, what should I do now? How should I fine-tune the parameters? So one thing, if you want to read more, I recommend looking at Goodfellow and Benjos and Coville's book, chapter 11 and 12. They have a very nice discussion about the practical implementations and the fine-tuning of the parameters. So what you would typically see is that many people actually use grid search with cross-validation to find the right hyperparameters. That is pretty common. And you can use a randomized search for the optimal parameters. That's also been done. And if you look at Keras and TensorFlow and PyTorch and all these packages, they do actually have a grid search for you of the optimal parameters. There's actually a tool which implements more complex algorithms to find a good set of hyperparameters, if you want to look at that. If you look at the number of hidden layers, the typical approach is actually you start with one hidden layer. And then you move to two hidden layers. And if there is no improvement when you move to two hidden layers, most practitioners will just stop with one hidden layer. So if you get, let's say, 100% score on one hidden layer, there's no point in moving to two hidden layers and increase the complexity, because then you've actually trained a neural network which gives a very good reproduction of the data. So these are the kind of things you need to consider when you're using a neural network or a deep learning method. So for more complex problems, you can gradually ramp up the number of hidden layers until you start overfitting the training set. So that's also something which can kick in, like you did with the polynomial approximation. So the kind of overfitting now translates into the number of hidden layers and the number of hidden nodes. Then there are many things which are useful to think of. So one thing, if some of you are going to reproduce experimental data with lots of noise, what you can do, if you have a good simulation tool which says something decent about what you expect, you would train a neural network on simulated data, which may not have noise. Then, instead of you starting with random values for the weights and the biases, you start with a pre-trained network. This is actually what has been done with ImageNet. So ImageNet is a pre-trained neural network with millions of images. And people have actually used that from the identification of cats, classification of houses or whatever, till experimental data from experiments which have been run at CERN. So you can actually have a pre-trained network which has some of the basic elements, and then you can apply that to data which may be pretty noisy. So that's something which is pretty common to use, to have a pre-trained neural network. Then there's always the question of the backpropagation algorithm and the activation functions. And in the project, you should try to explore at least one or two of these functions. And one of the problems we have is that of vanishing gradients. And the problem with the sigmoid function was actually one of those. And that almost led to the whole field of deep learning in the 90s and the beginning of this millennium to almost die out, because people didn't see that much use in neural networks because the training could stop. And the reason for that was that people were using the sigmoid function, which is pretty flat for large values of x for the input. And that means when it's pretty flat, it means the gradient goes close to zero. And you remember now that the gradient is proportional to the derivative of the activation function in each layer. And that means that if that vanishes, you end up in a problem with a network which stops being trained. And that's not desirable. So then people have cooked up different activation functions, as we discussed during the lectures. You have this ReLU function, you have this exponential linear units, you have the tanh function, which many people use, and so on. So there's a whole family of them. And this can drive you crazy. And many people would typically, when they present the result, you have always to state which activation function you have been using, which type of optimizers you've been using, because then people can actually reproduce your data. So that's pretty common in the literature, that you have to state which functions you're using. And then there's also the problem of exploding gradients. And with exploding gradients, there are many tricks to do that. One is actually just called chopping. That means that you chop off the results if the gradient is too large, and you put it back to a smaller value. And then you keep training. That's very ad hoc. But this is actually one of the techniques which is being used. And as I said, neural networks and deep learning is a pretty new field, and there is a lot of mathematics linked to it which needs to be explored yet. So I'm not going to go through everything here, but one of the authors of that textbook, Joshua Benjo, is actually one of the persons who had published that paper, which has more than 10,000 citations, just to mention that, which deals with the problems of vanishing gradients, and they link that to the sigmoid function. Until that paper came, deep learning was almost abandoned. And after that paper and how one could fix it, the field actually really exploded. So the derivative of logistic function, this is something we discussed some weeks ago, so you could actually look back at it. But I just wanted to say something about some other quantities or some other topics. There's something which is called batch normalization, and these are options which are included in many of these programs. That is a technique consists of adding an operation in the model just before the activation function of each layer, where you zero center and normalize the inputs, and then you scale and shift the result using two new parameters per layer, one for scaling and the other for shifting. So this operation here lets the model learn the optimal scale and the inputs for each layer. So that's one way of doing it. There's something which is called dropout. That at every training step, every neuron, including the input neuron but excluding the output neurons, has a probability P of being temporarily dropped out, meaning it will be entirely dropped during the training step, but it may be active during the next step. And then there's a new hyperparameter. There's something which is called chopping or just gradient clipping, where you simply put the gradient back to a smaller value if it just becomes too large. So if you go into, I recommend when, if you're a little bit bored, if you have a problem with your program and you have a bug which you can fix, take a look at these chapters 11 and 12 of Benjo's and Goodfellow's book, because that contains many of these kind of practical considerations. So at the end, what you end up, even if you have this beautiful universal approximation theorem, we end up fixing many parameters. The kind of overarching message, which you will see in many articles, is that you first try to tune the learning rate and the hyperparameters lambda. And then when you found an optimal accuracy, then you start tuning the other parameters like the number of epochs, the number of batches you have, or if you're doing a stochastic gradient descent with ADA-grad or things like that, you would tune the parameters of those specific methods. But the overwhelming parameter is normally the learning rate and the hyperparameter. These are the ones which are the most important parameters in the training. Clearly also with a number of hidden layers and neurons in a neural network. So I propose we take a small break, if that's okay with everybody. And we just come back in 15 minutes. So the topic which we are going to switch over to now deals with, first we're going to have a quick look at the top-down perspective on neural networks. And before I do that, I actually need to change my settings on the audio, because it seems that my headset is not functioning well enough for those of which you are online. So that should be connected, but let's see now. Okay. Just a small okay. Minor thing here before we proceed, and let's now see if I have back my audio here. Yeah, so those of you online should be able to hear me well now. Please let me know via the chat whether you're not hearing me. Okay, so the neural networks, all the things which we have been discussing before the break, some of these are actually summarized here. And there's a lot of pros and cons. The strength of deep learning methods is the universal approximation theorem. which states that you can actually approximate a continuous function to a given error with at least one hidden layer. The universal approximation theorem doesn't say anything about the number of layers or the number of nodes or the type of activation functions and so on and so on. So that means that many of these parameters are parameters which we need to explore. So the way I tend to look at it is that when I run a calculation with deep learning methods, I look at this as an experiment. And then I repeat the experiments and repeat till, and you obviously have to strike a balance between the amount of time you have, the number of cycles you want to use, and the quality of the results you want to have. But then you reach a conclusion with these and these settings. And this is essentially what you will be actually doing in project number 1 and number 2. And if some of you is tempted to try the Franke function or the topographical data, you will actually see that the neural network can outperform the polynomial fit, which I did in project number 1. Another thing you should be a little bit careful with in project number 2 now, if you're looking at a polynomial which are fitting. In project number 1, your design matrix reflected the polynomial or the complexity. That was the way you defined the complexity of the model. Now, when you deal with neural networks, you should not feed in the polynomial degree, because then your neural network will try to fit a polynomial to a given degree. And that may not be the function you're looking after. So just keeping that in mind, that when you're doing a regression problem with neural networks, you should just feed in the input variables, the x's or if you're in 2 dimensions, x and y, and so forth. So this is it's a kind of philosophical concept. So we also have what is normally called a discipline-informed input to neural networks, where you could inform the network about specific properties of your system. So like I'm doing quantum mechanics with neural networks, and then I would typically feed in the positions of particles, the relative distance between particles, and so on. So that would be what I would call physics-informed deep learning. But this will vary from field to field. But like in this case, when you're fitting a function, you should try to avoid to repeat what you did in project number 1. You can do it, but then you're in a way giving a bias to the network, and the network is trying to reproduce that polynomial you have decided upon. So it's fully possible to do that, but in a way, you're then not using the full strength of the universal approximation theorem, where you actually let the network find the best representation of your function. But just give it a thought. I mean, you can choose both and make a comparison. Actually, people have, during this project number 1, the nice thing with the working on projects is that people really can go on along a tangent and explore things they found interesting. And we like that. So when we grade things, if you have a specific story you want to tell, which you found interesting, that is much welcome. And we discussed during the break, we had people last year, which for project number 3, discovered several things with the gradient descent methods. And they did define a project number 3, which dealt with the explorations of different gradient descent methods. So that's fully possible to define such a project number 3. Okay, so if you take a top-down perspective on things, when we see the calculations here, we typically have a training set, a validation set where you normally fix the parameters, and a test set. You should think of, again, doing cross-validation when you look at your data. And typically you would estimate an optimal error rate. You would minimize underfitting on training data set, and also make sure you're not overfitting. So these are the same things which pertain now to a neural network as it did when you were doing a linear regression in project number 1. There are things which we do not cover in this course, and that's about the quality of your data. It means that we often will have a nice type of vanilla data or data which have already been prepared for you. So like the cancer data, which you have as an option in project number 2, is already well defined and well prepared. There are no errors in the data set. But if you want to use your own data set, you have to be a little bit careful, because you can have data sets which have been collected at different times. People may actually have used different units. So we had a case where we had units in kilometer and units in meters per second and kilometer per hour, and that created a lot of confusion. That happens. So these are things which you need to be a little bit aware of. And if you look at the limitations here, the methods which we are looking at till now are all methods which fall into the box of supervised learning methods, which means that we need labeled data. Labeling the data is expensive because somebody has actually to traverse the data. And if you have millions of data, people have actually to decide whether this is a cat or dog or whatever kind of thing it is. So that means that labeled data is an essential part of a neural network. And you need to have the neural network is actually extremely data intensive. And you will see that the more data you feed in, the better the network is doing. But then clearly there's always a balance you have to strike. Another thing which is not so good with a neural network is that they normally require homogeneous data. That means it has to be a data of one given type. So when we move to methods like decision trees and random forests and methods like that, then we have the possibility to deal with heterogeneous data sets. But neural networks are actually much more rigid in that sense. And many of the problems are also not about prediction. And often in natural science, we're interested in learning something about the underlying distribution that generates the data. And in this case, it's often difficult to cast these ideas in a supervised learning setting. So, but it's possible to make good predictions with a wrong model. And the model might or not be useful for understanding the underlying science. So you can actually have a wrong model, which gives a perfect fit to the data. So the model optimization is a topic which goes more into the field of Bayesian statistics and model optimization. This is not something we cover in this course, but just be aware of that. So if you're more interested in these topics, we do actually have courses at the university here where they deal with model optimization. Another thing which you will see as a disappointing part in neural networks is that many of the activation functions, they're just given in a way by a kind of almost ad hoc-like function. They are often defined because they are easy to calculate and they are easy to obtain the derivatives from. And you will see that when you're setting up the training of the network. If you have a complicated function, then clearly the derivative becomes also complicated. So there's a kind of trade-off there. And there is a new field, an emerging field, which is called Bayesian machine learning, where you actually find a probability distribution for a given activation function. But that becomes much more expensive from a computational point. But this is actually a very interesting research field, where you combine the best of the deep learning with a Bayesian statistics approach. So these are just things to think of for more advanced courses. But you should always, sorry for going off on a tangent today, but you should always try to keep these things in mind, because understanding the pros and cons is essential when you want to make improvements. Any questions so far? Things which are unclear? Because then I would like to switch to a new topic or an application of neural networks. And this deals with the solution of differential equations. And this is a topic which many of you may be interested in, because in natural science, we often deal with solutions of differential equations. So I just wanted to bring up a quick reminder of a typical way by which we solve differential equations here. And before we move on, there's a question in the chat. Yeah, okay. So there's a question in the chat whether we could repeat what we said about the letting the network find the best representation of the function. So let me just repeat that, because this is also kind of partly philosophical. So we have the universal approximation theorem, And that states that the neural network should be able, with at least one hidden layer, to find the best possible representation to a given error of a given function. So the network is then trying to find the optimal parameters which reproduces this underlying function based on your input data and your output data. Now, if you condition the input data like you did in project number 1, where your model was defined by a polynomial of a certain degree, then your design matrix reflected that. And you were simply using linear regression to find the optimal parameters for a specific polynomial. Now, if you send that into a neural network, you are in a way conditioning the search for the optimal parameters, because then the network is trying to find the optimal parameter for the specific polynomial you have decided to study. And in a certain sense, then you're defying the strength of the universal approximation theorem, which simply says that a neural network with one hidden layer is capable of finding the best representation of a given function. I hope that helped a little bit. Yes, so when it comes to project number 2, you should rather put in your design matrix the x values if you're dealing with a one-dimensional function, and that's it. If you have a two-dimensional, it's x and y. So you would have one x value, one y value, and that gives you a final z value, for instance. Okay, so the thing which I wanted to look a little bit at now is the solution of differential equations, because that's pretty neat. And you will be surprised to see how simple it is actually. So let's switch a little bit to the whiteboard here and take a closer look at that. So if you think of a differential equation of the first order, so let's now look at neural networks and differential equations, NN, neural networks, and ordinary differential equations. Or normally what we call ODEs. And if we look at a first order differential equation, a typical example would be something like d of y of x of d of x is equal to some function f of x. And since this is typically a first order differential equation, and it's an ordinary differential equations, we have only initial conditions. We are not dealing with boundary conditions. So as soon as we move beyond one dimension, we would typically have both boundary and initial conditions. And then we move into the world of partial differential equations. But let's stay with ordinary differential equations first, because that's the simplest case we can look at. And typical way we would solve this numerically is something like Euler's algorithm, which is the simplest possible one, which we should avoid, by the way, especially if you have energy conserving quantities. But you can use simple modification like Euler-Kroner. I guess everybody's familiar with Euler's method, right? But let me just quickly remind you of Euler's method. So what you would typically have here is an initial condition. I hope you don't get offended if I bring these things up again. So you would typically have some f of x0, which has some specific value, which we just call f0. So that would be the initial condition. And x could then be defined in a domain from x0 to some final value x of n. So this opens up for discretization already when I do it like this. And what you would do then is to discretize. So you discretize x over to an x of I, which you would typically define in terms of the starting point, plus some step size, delta x, multiplied with this parameter I, and where this I goes from 0, so you have discretized now up to n. And this delta x is normally called a step size, and that's given by the last point minus the first point divided by the number of integration points, or the number of mesh points, or the number of grid points. So there are many different names for that. And then you would discretize the function y. So you would also have y, which goes over to y of x of I, and this is equal to y of I. In principle, I should have used another function, another symbol, because the discretized version is not the same as the continuous version. So often in mathematics text, you will see different symbols. But I am a sloppy, poor practitioner of mathematics, so then I just use the same symbol. Then what you would have next is a function f, which is also discretized, and that is given by f x of I, and that becomes equal to f of I here. And now in our case, when we discretize, we can then make an approximation to the derivative, so we Taylor expand over function x, no, function y around, and then we can choose some x of I plus minus delta x. And if we do the plus delta x, we obtain what's normally called Euler's forward method. So let me just bring it up as one of the simplest possible methods we can look at. So if we do that, what we get then is that our y of x of I plus this minus delta x here is obviously given by y of x of I plus minus delta of x, and then we have the derivative of y at x of I plus delta squared, so delta x squared divided by 2 factorial, and then we have the second derivative of the function we are looking at, y, second derivative evaluated at x of I, plus this delta x to the power of 3. So these are the remaining terms there. And then if I truncate away the second derivatives, we can then get an approximation. And if I now take the plus sign, I take a plus delta x, I rewrite that as a y of I plus 1, just one step size. I can approximate that one with y of I plus this delta x multiplied with y derivative at the point I. So this is approximation when I leave out the second order terms. And y of I, the derivative, y of I derivative at x of I is actually given by this function f of x of I. So this is one of the methods we are going to use to compare the neural network with. So this is the same as our f of I. So that means that what we can say now is that y of I plus 1 is equal to a value y of I, which we would typically use as the initial value to start the calculations. We start at x0, and then we integrate up. So we get a plus a delta x multiplied with f of I. And that's Euler's forward method, or forward Euler. You can introduce more advanced methods. You can do Euler-Chroma, you can do Runge-Kutta to different orders, and you can actually have a plethora of methods which you can implement. But this is the simplest possible one, and we're going to compare the neural network with that one, and also slightly more refined methods later. Now, when we deal with a neural network now, what we need is obviously to satisfy the initial conditions. So when we look at the equation which we had, if we now go back to neural networks, so what we have is an equation of the type dy d of x is equal to f of x here. So if you now were asked, how could you use a neural network to solve that equation? What is your feeling? I mean, what would you, suppose now I am a person who's been working with neural networks and I have a fancy code, but I don't know what to use it for. And you come and tell me that now you can use this for solving differential equations. Suppose you're giving this problem here. So how would you solve? Actually, the answer is pretty simple, but it requires a little bit thinking. How would you actually solve a neural network problem, a differential equation problem with a neural network? How could you define a cost function? Yeah?
You just move the f of x over and say it's equal to 0.
Yeah. It's actually, that could define your cost function, or you could square it if you want to. And so what you would do then, if you look at the left-hand side and the right-hand side, you take the difference between the two. You start with an initial guess, but you should give some constraints. And the constraints are that you should obey the initial conditions. So in our case, we have an initial condition, and if you move to partial differential equations, you would have the boundary conditions in addition. So you need to have a constraint, and that is your information to the network. And then your cost function is now going to be the difference between the left-hand side and the right-hand side. You can square this quantity so that you amplify outliers, and then you would simply iterate till this difference is as close to 0 as possible. And that's where you would stop. So that means that your ansatz for the function, your y, should now be given by a given neural network. And that network is given by the complexity of your architecture, the number of hidden layers, the number of neurons, the number of, or the type of activation functions, etc., etc. So the basic philosophy, so let's just look at this from a more overarching point. So the basic philosophy is to take the difference, is to compute a cost function which is the difference dy dx minus f of x. You can take the absolute value. If you want to connect with the mean squared error, you could actually square this quantity if you want to do that. So this is something which would then be defined by the points you have, the discretized points. So your input to the network will be the x values. So if you now look at the discretization you have done and the examples we're going to run now, they are going to contain this discretized set of x values. This is going to be my input. And then I need to input also when I'm setting up an ansatz for the network. So for the function y of x of I is now going to be represented by a function which I'm going to call y 0 tilde plus an nn function which is going to depend on x of I and the parameters theta. So this is our neural network. And this is a function which obeys the initial conditions. You can, if you want to, you can inform the network in a more advanced way. If you know that the function is, let's say, an exponential, then you know that there should be at least some dependence of x. So you could take x multiplied with the neural network, because you know that an exponential goes like x plus x squared plus x cubed and so on. So you can always inform the network in some specific way. But you need to plug in the initial conditions, and then you have the network, which then is supposed to find the best possible representation of the difference between the left-hand side and the right-hand side. And typically what you have is normally a derivative on the right-hand side, which either has an analytical representation or is a function which we know how to compute. So that's pretty common when we are dealing with differential equations, because a typical setting is that we have an expression for f of x here, but we don't know why. So if you're dealing with a, let's say, a type of Newtonian type of problem, then your f of x could be the acceleration and your y could be the velocity, just to give you a simple example. And if you have a model for the forces, you know what the acceleration looks like. So that means that typically the right-hand side is something you can compute, and or you have a function which is something you could evaluate using gradient descent, just to give you an example. So let's look at how we can implement this. I mean, this is the basic philosophy. And the implementation of that is something which you will find in the slides here. So let's just go back to the slides, to the Jupyter notebook, which is a little bit better. And this is now the Jupyter notebook for this week. So solving differential equations. So we are going to look at that one. We've gone through TensorFlow. And if we reach the topic tomorrow, which is convolutional neural networks, we will start with that. But let's take a look at the implementation of solving differential equations. And this is actually something, some lectures which were developed by a former teaching assistant here. And some of you may have met Christina. By the way, if somebody is looking after an extra job and you want to improve the codes which you see here, let me know. And I have some additional money for that. So if you need a small extra job, please let me know. That's just a small announcement. I'm gonna send an email to everybody, right? So that not only those of you in here will get that message. But if you need some, let's say if you want some month of extra work or up to 2 months, we can easily do that. Okay, so typically, if we now want to make this more abstract, we would have a differential equation which has is a function which depends on an input x. There may be a function g of x, a derivative, a second derivative, and so on. And we are typically putting that one equal to 0. So this function here, what we are doing now is setting up the difference between the left-hand side and the right-hand side of a differential equation. So this is the more general representation of what you saw. So you have some kind of function, which is now the difference between the left-hand side and the right-hand side. And it depends on various types of derivatives. This is a general structure of a differential equation. And gives you a slightly more abstract way of representing what we put on the whiteboard. So what you would do then is to let your trial function or your trial solution to be represented by a function here, which has the initial conditions, if that is an ordinary differential equation or given boundary conditions. So you want your function to satisfy these conditions. And then you have n here, which is a neural network with weights and biases described by this quantity p. And then you have a function here, h, which takes in x and the neural network. So this is the basic assumption which we are going to make. So if we now look at the minimization process, and we don't need to go through this, we can actually look at the explicit example. And this is the one you will see in the first code here. So we have a function, the derivative of function, which is simply given by the function itself times a parameter. And this is just the standard equation for exponential decay, which I guess everybody learned to solve even in kindergarten. I guess you now solved that in kindergarten. You did solve that in kindergarten, right? You did. I have great thoughts about you guys, especially looking at project number 1, which was impressive. And then the function to solve is, so this is the function, and we would have some initial conditions, G0, and with gamma just being some chosen values. And in the example here, I've chosen gamma equal 2 and this G0 equal to 10. And we need to choose a solution here, and then we need to set up the network. So this actually is a little bit repeat of what we have done. And so we need a hidden, define a number of hidden parameters, the number of parameters in the output layer. And in this case, we're just going to run it with one hidden layer and an output layer. And I'm not going to repeat everything here because this is a kind of repetition of what we discussed in the previous lecture about the setup of a neural network. So this is about the architecture. And the problem now becomes this is given now by these initial conditions. And then I'm actually going to put in a dependence on x here because I know that my function being an exponential has at least an x dependence. You don't need to put in that, but this is going to speed up a little bit the iterations here. And the difference, the cost function which we're going to set up now is actually the difference between the left-hand side and the right-hand side, and we square it, so it looks almost like a mean squared error. And then we just keep iterating till this difference is as small as possible. And you can now see, if we just scroll down here a little bit, so you don't need to look at all these details because this is actually the same details which we have for the setup of a differential equation. So we use plain gradient descent here. And if you look at the code here, we have for the intermediate layer, we have the sigmoid function as an activation function. We plug in number of hidden parameters for the weights, for the outputs. We need to set up the dimensionality of the input array x. So this is the input. It's simply the x values, which we have defined. And these x values are given now by a grid of values. And then we keep going and define the set values for the hidden one, which is simply the unknown weights, which we have initialized, multiplied with the inputs. The output from the hidden one is actually given by the sigmoid function, which modulates the input here, which is now given by these values here. And in this case, I didn't put a bias. You could have put a bias here, but I'm just doing this in order to stay as simple as possible. And then you see now the output layer, and this is something one of the reasons why I bring this up is that this can also be useful for you when you're doing the regression problem in project number 2. Because you see now that the output is not modulated at all by an activation function. And this is the standard when you deal with a regression problem. And you see now that I'm setting up the hidden one, and I simply perform a multiplication output weights multiplied with the hidden inputs, the input from the hidden layer, and that gives me the output, and my output is just given by these variables. And then I have a trial function, which is now given by this in G0, which now gives my initial conditions, and then it has x times the neural network with the parameters and the values of x. And this is the right-hand side of my cost function. This defines my cost function. And that means that I have, this is the right-hand side, and my cost function is actually the difference between the two. And here, you can actually use automatic differentiation to find the derivative with respect to x of the neural network and find the derivative with respect to x of the trial function. So in this case here, I've reverted to using automatic differentiation, which I normally recommend strongly to use. That saves you a lot of time. So remember now, one of the reasons why we use automatic differentiation, there are several reasons for that. One, calculating derivatives by finite difference is error prone, and it requires also a lot of cycles. And you will see that if you calculate the second derivative of e to the x, you will not get the exact value. If you do symbolic manipulations, like if you use Mathematica, sometimes it can give you a very complicated expression, which will require a lot of floating point operations to implement. Automatic differentiation gives you, through the application of the chain rule, derivatives to numerical precision. And it's an extremely efficient algorithm. And if we run it, so what I've done here is to define the error as the difference between the left-hand side and the right-hand side. And it simply returns the sum over these. And then it calculates the 1 over the number of data points times this sum which we have here. And if I run this, and I run my network, the initial cost function, this is the difference between the left-hand side and the right-hand side with the initialization which I did. And this is not something you would bring to the next party. So if you come to Friday evening with this kind of cost function, maybe they won't let you in again next time. But then you can see now that the max absolute difference which you have, and this is the final cost function, which is not bad for such a very, very simple implementation of a neural network with just one hidden layer, very few hidden nodes, and then just setting up a guess for the function. And tomorrow we are going to look a little bit more at this before we then move over to the next topic, which is going to be convolutional neural networks. Now, when it comes to convolutional neural networks and recurrent ones, we are mainly going to scratch the surface. And the reason for that is that we do have a course which is called IN 5400, which runs in the spring semester and which uses this course as an input, and we have to avoid credit overlaps. So that course actually goes into the very gritty-nitty details of convolutional neural networks and recurrent ones. And I normally recommend, if you're interested in these topics, to follow that course. That's an excellent course, by the way. Okay, I'm going to stop here, if that's okay, and then we continue tomorrow with some more applications of applications to differential equations, and then we start with convolutional neural networks. And then this is going to stop the recording today.